The engineering department has been hard at work designing the next phases of transmission pole replacement projects. This project involves the replacement of transmission poles beginning at Airport Substation, along Highway 101 through the Tumwater Valley, up along Lauritsen Boulevard, past Ray Street, Franklin Elementary and Crestwood, going all the way to the BPA substation in Port Angeles near the college. Traditionally, a program called AutoCAD has been used to design these projects. In the fall of 2019, the district purchased a program called PLS CADD, a program made specifically for the design of transmission lines. PLS CADD is a superior product in this case because it is a three-dimensional model of conductors, poles, insulators, and other equipment used. It is a three-dimensional model of the ground terrain underneath of our conductors. It is a smart design, changes propagate across the entire model. It is an accurate description of the components used in the model, including material properties of poles, conductors, and other elements. The program is then able to do what is called a finite element analysis, whereby loads are placed upon the equipment, and by checking against the material properties, it can determine whether or not that equipment will fail or not. And changes to the design are very easy. This project has some unique challenges in terms of the loadings that our structures will see. There are 4 8 structures for long crossings through the Tumwater Valley. There are 5 poles with City of Port Angeles utilities on them, including distribution and transmission, and there are 8 poles which share transmission lines with McKinley Paper. At 1,264 feet and 772 feet, the long valley crossings through the Tumwater Valley are particularly challenging because we want our conductors to always stay up under all weather conditions that might be seen. In designing these projects, the goal is to ensure that the conductor clearance to ground and other structures always meets the minimum distances as specified by the National Electric Safety Code. Conductor sag can change quite a bit as the temperature changes. For example, if we were to look at a 1,260 foot span of 556 ACSR conductor between 0 and 120 degrees Fahrenheit, the sag will change over 12 feet. Conductor sag will also change depending upon the type of conductor used. Here, looking at a 556 ACSR conductor, which is an aluminum conductor with a steel core, as compared to a 556 AAC, which is an all-aluminum conductor, on a 300 foot span, the difference in sag between 0 degrees and 120 degrees Fahrenheit is 1.6 feet difference between the two of them. The tension of the conductor will also change as the temperature changes. For example, on a 300 foot span of 556 ACSR conductor, at 0 degrees Fahrenheit, the conductor is pulling on the pole with a force of 6,426 pounds. At 120 degrees Fahrenheit, it's pulling with a force of 2,182 pounds. With 7 conductors per pole, 3 transmission and 4 distribution, that equates to a force at 0 degrees Fahrenheit of almost 45,000 pounds, or 22.5 tons pulling on our pole. At 120 degrees, that force reduces to 15,000 pounds, or 7.6 tons. Wind and ice loadings can significantly increase the total forces that the conductors and poles see. As you can see, conductor sag, which affects ground clearance, and conductor tension, which affects pole strength, varies quite a bit and depends upon the type of conductor used, the temperature, and additional loads and wires. All will behave differently. The PUD has construction specifications which dictate the minimum distances between all pieces of equipment placed upon the poles. Our construction standards specify from the top down the minimum distances that each piece of equipment must be placed. From the bottom up, we then also have design clearances that we're looking to maintain. 32 feet for transmission, 27 for distribution, and 20 for communications. In order to properly evaluate clearances, we need to have an accurate profile of the ground line underneath of our lines. With the ground profile established, I can offset that ground profile by the minimum distances we're looking to maintain based on type of conductor. We never want to see the conductor sag interfering with the ground profile. That would be a violation. The conductor sag must always stay above the ground profile at all times. Traditionally, this information was collected by a manual survey. A manual survey is very labor intensive due to the large amount of data that must be collected, and it's also potentially dangerous to the surveyor having to work on busy streets. In 2019, the district began employing the use of LIDAR to collect this information. LIDAR stands for Light Detection and Ranging. An airplane flies over the corridor we are looking to map, shooting a laser at the ground. That light is reflected back to the airplane, and by measuring the time it takes to reflect back, they are able to determine a distance and thus accurately model the ground surface underneath. This information is accurate to within 6 inches. What this LIDAR data gives us is millions and millions of points in 3D space. Taken all by themselves, these points don't look like much. But as we begin to zoom out, you can see they begin to take on a form. Rotating the model around in 3D space, you can begin to make out the contours of the ground underneath. Here we're looking at the Tumwater Valley and the flat road surface of Highway 101 running alongside it. From all of the LIDAR ground data, we can infer what happens to the ground contour in between each of those points. From that, we can create a very accurate 3D representation of the entire ground surface. Once again, here looking at the Tumwater Valley with the Pine Street entrance coming into Highway 101. As you can see, taken all together, these points begin to create a very accurate description of the ground profile underneath. The LIDAR data is also able to give us above ground information. Because there is so much more stuff there, there's about 10 times the amount of data. Once again, looking down at it from the top, it doesn't look like much. But as you begin to rotate it in 3D space, you can begin to see trees take form, our conductors and poles take shape, even down to the buswork inside of airport substation seen here. From the LIDAR data, we're also able to see existing structures and conductors. From this, we can calculate what the existing attachment heights are or what the existing sag of the line is, should we need to know that. All of this from millions of points in space. Once the ground surface has been created, it is time to start modeling, first by building the poles. All of the different types of poles and structures that will be used in the design must be modeled. Here we're looking at a simple tangent transmission and distribution pole. Here we have a double dead-end transmission and distribution pole attached with a span guide to a secondary span guide pole. Here we are looking at one of the 8 structures that will be used in the long valley crossing through the Tumwater Valley. This structure requires many guys to make it strong enough to properly sustain the conductors under all weather conditions that we will present to it. We are also able to model equipment attached to the pole. In this case, the square boxes represent a transmission switch. This is important information to have because the switch can add additional load under wind and ice conditions besides the weight of the switch itself. Once all the various types of poles and structures have been created, I can begin adding them to the model. Survey points indicate where each pole will be placed, adding the type of structure at that location to the survey point, and changing it for the various different types of structures that will be used as we go down the line. Next, it is time to add conductors to the model, selecting from wire files that have the material properties for each different type of conductor used in the model. Now it is time to begin stringing lines. Lines are strung between dead ends, here attaching a transmission line section between 4 structures. After stringing the wire, we select the type of wire that will be used, 556, select the voltage level, 115 kV, set initial conditions for the wire, and we now have our transmission line. Going on to add the distribution lines, again between dead ends. Once again selecting the type of wire that will be used, selecting the voltage level, setting the weather conditions, and in this case changing it to a blue color to differentiate it. And you can see that now we have the distribution conductors strung. Once all of the different types of pole structures have been placed into the model and conductors strung, you can see that we now have a 3D representation of the entire transmission line and all of the various structures used within it. We're also modeling any other lines attached to the poles, as they will have an effect on the forces that each structure must withstand. Now, when we combine everything that has been modeled so far together, we finally have a full 3D model of our conductors, poles, and ground underneath of it. Here again, looking at the Tumwater Valley and all the various structures that go through there up to the top of the hill by Oak Street and SARS Grocery. Here we are looking at the portion of the line on the eastern end of the project, starting at Ray Street on the left going along Lauridsen Boulevard in front of Franklin Elementary in Crestwood, where we have McKinley power lines shown in purple attached to our structures as well. Moving on up to the end of the line where we turn 90 degrees and go into the BPA substation. Here you can see the Port Angeles Eastern feeder coming in on the right, the Western feeder, of which we're rebuilding, coming in on the left, as well as the McKinley lines also coming in. Now it is time to evaluate the design. We do this by establishing our design criteria, evaluating conductor clearance to ground, and finally evaluating the strength of the poles. First, we define the weather conditions that we want the model analyzed under, defining the various weather conditions, which are unique to our particular part of the world, and defining extreme conditions such as 90-mile-per-hour winds, or in the case of the Tumwater Valley crossings, we don't ever want those conductors to come down, so we're designing such that if all conductors ahead of that valley crossing were to come down, the poles would still stay standing. Now it is time to evaluate conductor clearances using worst-case sag for our clearance check. Now that we have everything modeled, we can begin analyzing. Here, looking at the profile view, the dashed lines represent the ground clearances we're trying to maintain. I can now evaluate conductor sag under various temperature conditions. Here, we're looking at 0 degrees Fahrenheit. I can change that to 120 degrees Fahrenheit and you can see the conductor sag change. Or take it all the way up to 212 degrees Fahrenheit and the sag changes again. Next, we must correct any sag violations, where the conductor has sagged below the ground profile, thus indicating an interference. Where there is an interference with our sag, such as here where the distribution conductor has sagged below our minimum design clearance, I can then go in and change the pole in the model. Here, changing it from a 70-foot tall pole to a 75-foot tall pole. By changing it, the conductors raise up and we now clear. Finally, it is time to evaluate pole strength. Is the pole going to be strong enough to do what we are asking it to do? A color gradient shows whether or not the pole will fail, with anything red indicating that it has exceeded the material properties and thus the pole will fail. Now it is time to begin checking structure strength. The program goes through and evaluates each pole, and the color gradient shows us whether or not it passes or fails. Here, the base of this pole is turned red, which means it has failed. It's not strong enough. I can correct this by going in and changing that pole out to a stronger pole. In this case, changing it from a class H1 to a stronger class H2 pole. Having replaced the pole, I now do a structure check and I can see that that pole now passes. This structure, with the two City of Port Angeles transmission spans attached to the top of it, will need to be particularly strong to support all of the conductors that are attached to it. When I analyze the structure doing a structure check, the program will tell me here that it has failed. By analyzing the deflection of the pole, which PLS CADD shows me how it deflects under the forces placed upon it, I can begin to figure out how to correct the problem, either a stronger pole or adding more guys. PLS CADD also allows us to evaluate unusual conditions such as galloping. Galloping is a phenomenon where the wind blowing across the conductors causes them to begin swinging around in large circles, potentially causing the conductors to hit, a condition we want to never have happen. When analyzing for galloping in the PLS model, the program draws circles to describe the path the conductor will take as it swings. In this case, you can see that they're all red, which means that the lines are interfering. We will have to install spacers. We can also evaluate the design using Google Earth imagery. This allows us to get an idea of how the line interacts with the environment around it. Google Earth imagery is imported into the model and shown underneath of the transmission lines. This imagery allows us to get a good visual of the entire corridor and what lies underneath and around it. We are also able to show easement and right-of-way boundaries to ensure we stay within the area we are allowed to occupy. Next, it is time to create construction drawings, giving plan and profile views needed for construction. Traditionally, this was AutoCAD and all manually drawn. PLS CADD makes the creation of construction drawings very simple. From the 3D model, plan and profile views are automatically generated and sheets are created for the entire project line. PLS CADD also allows the 3D model to be exported to a Google Earth file. With the model exported to Google Earth, this file can now be given to vendors bidding on the project. To give them a very clear idea of what it is they're building, and also enable them to get some idea of the challenges they may face in terms of terrain and structure along the way. This file can also be useful for construction crews on site to be able to use as a reference at each location to see what it is that they will be building. As you can see, PLS CADD is a very powerful design tool. It is very accurate and greatly simplifies the design process. Thank you very much for your time. If you have any questions or would like to know more, please feel free to contact Ben Phillips in Engineering.